yeah, then let's start with the second talk for today. And thanks, Stefan and Erkan. I jumped in for someone else. It was planned that I have this talk later in the year. So we will talk today about your prompts hits the wrong pot, 96,000 tokens, and you start from scratch. And we will figure out what this means. And at the beginning, we're starting with a working GPT model from scratch. I show you a GPT model, and you will see in action what Stefan already told you in the last session, right? So you will see a lot of things you already know now. So let's start here for a little bit. So I have here in very straightforward GPT-2 implementation, also written in PyTorch, right? So, and technically, what we're trying to do here with this GPT-2 model is we want to send it a prompt. Let's say, was ist Kubernetes? And then we want to get from this GPT model like the next 10 tokens. And we also will increase give me 200 tokens. And then you will see that it gets slower and slower and slower that we can get the tokens. But first of all, let's have a look what happens if we sending this from my terminal here. So it's in KV Python implementation here, and we're sending the prompt and then we're requesting the tokens. So first of all, what we're doing is we're getting the prompt, and the first thing what we're doing here, we're generating from this prompt tokens, right? Because these are the tokens we're getting or we're giving the model via the generate functionality. So that's the first thing. And you see here, I have a GPT without KV cache because that's what we want to see, let's say in 25 minutes. What does it mean? And basically what's happening is we're becoming here in this generate definition, right? And you see here something we called max new tokens, right? So we're ranging technically over the amount of new tokens. And what's happening here is we're getting all the time the full input IDs. So from our prompt, the IDs, and we're looping here over again, right? And technically, we're interested here in the last token, right? So we have a sentence, right? We have tokens out of it when we want to generate the next token, what Stefan already showed, right? But the bad thing, what's happening here is because we're ranging here over again, is we have a new token, we're sending it again, right, in the loop, and then we want to generate the next token. But we have all of the computation again and again and again. And this is happening on a few areas in this implementation, right? So from this generate step, you see here, becoming then, because it's happening in PyTorch that we're coming from the generate now here to the GPT forward. And this is what also Stefan showed you already. So the embeddings here gets recomputed for the full sequence in every step too. This happening here. Then we're entering a next step. We don't need to understand everything from here, but we have the next thing called block forward, right? And we're calling this per layer inside, right? So what Stefan you showed with all the layers, and we're doing this.
One red box. Basically.
Yeah, one of the red boxes, right? Different layers. We're doing this here. And then again, we're going here to the forward, to the attention. We enter the step 4. And then you will see we have here this attention forward, right? And here is our QKV work. And we will see in a bit what this means. So for now, that you can trust me that everything is working, let's run against this GPT-2 implementation. We have a prompt and we want to see the next 10 tokens. And what you can see is this model at the moment is bad trained. The weights are not correct. But what we can see here is we basically have a prompt from was ist Kubernetes. These are 6 tokens in the input, right? And then we ask for 10 new tokens, and this 10 new tokens basically 6 words, right? And that's what we're getting here. The interesting part here, what happens is you see with 10 new tokens, you see roundabout for every token, we need 2 point something milliseconds for the computation here in general, right? And let's make this for a second for 250 tokens. And if you're running this for 250 tokens, you already see that the time is growing, right? And the more tokens we're requesting now, the worse thing happens, right? So you see it's growing and growing and growing. And this is if you chatting today with like your Chat GPT, your Claude, right? And sometimes it's waiting and you have the feeling of something is stuck, right? Then you have the feeling, then you can think of something is going on with the cache implementation on their side, perhaps, right? And we will see in a bit how this cache in general works here. So first of all, let's start the presentation again. So what I showed you is from my basic ChatGPT or from my GPT-2 implementation, the code works. It was trained, right, and it generates texts, right? So, but it's totally inefficient because we're seeing the more tokens we're requesting, it's getting slower and slower, right? And this is because of our redundant computation. I showed you the for loop with the max tokens, right? And for every time we're recalculating here the full sequence from all the tokens to get the next token. And this is here because of our implementation in the attention part of the model. So Stefan already showed you that attention QK and V equals softmax QK over T and over the square root of DK plus mask and the V, right? And you can think here a little bit of that QK and V is essentially something like a search procedure, right? What Stefan showed you before, right? So you're trying to figure out the token and you're searching against every other token to find similarities, and you have the weights, right? And if you have the similarity and the weights, then this is what we want to get from the new token. So you can say for query, for example, we asking something, for the key, we offering something, and for the value, that's the content we're getting back, right? And we will see that everything which is like the waste in the current implementation is here around because we recomputing every time the full sequence to getting the new token. So that says our bottleneck here is, as I said, the recalculation of the key, and in the code it's called K, and the value V vectors, right? So you see in the code, if you're looking in a few seconds ago inside, that there's K and V's, and this is what we're recalculating. And
I didn't show that, but I should have. The table which gets information about cat and sit and so on.
Yeah.
Table is basically the Q value here. And what the other tokens in front of it offer in this query, right? It's always the same. In every completion step, like every next token, it's always the same what the words in front offer.
Yeah.
And what they offer, this is the K, and what the value is as a data transfer, it's always the same. That's why K and V we can cache, because it doesn't change anymore.
I have a little bit and go over it, right? So the cool part is we could implement a KV cache here, right? And technically that's the foundation of every modern LLM we see today outside, right? And everybody is like taking care and around this implementation. So when what you can see here, it's not hard to implement the KV cache in the model, right? So you see, technically it's like something around 20 lines of code changes. It's a bit shorter here because otherwise it's not visible here on the screenshot. But I can show in a bit how this technically works, and then you will understand the screenshot at the end. So technically, again, what I already showed here with the range of max new tokens in the for loop is at each step we pass the entire sequence here, right? So this IDX, what we're getting here at the beginning is our sequence, right? So that's our prompt we're setting. Was ist Kubernetes, right? And this is what we're getting here, and we're requesting new tokens. And with this logits equals self IDX, we doing this full calculation here, right? The computation, and then you see the waste here, right? So we're doing all this expensive computation here, but we're only taking care of the very last token here, and that's the new generated token, right? And that's what we're putting then here in our softmax implementation. And at the end, we looping it now with the next token, and then we're doing it all over again for the 5th token, for the 6th token, but we're generating everything again. And in the attention mechanisms, it looks very, very similar because we have, again, in the attention implementation here, dx, and dx is, again, the full sequence, right? So the length of all the tokens. Means if you have like buses Kubernetes, and let's say that sequence t is equals 3, right? And then we have the next token, then it's T4, T5, T6, and so on and so forth. And we have the full input sequence here to get like the Q, the K, and the V, right? And again, we can also use here the KV cache if we would have a cache implemented here. So that says, that means the loop repeatedly calls the attention, and everything is almost identical, right? Because it's with more tokens. It's all the same thing what we're doing all the time, and we redo all the work. And this is like really wasteful on our GPUs when we're using it, right? Because we're blocking the full GPUs later on to doing like the wasteful work of time. So to make this a little bit in pictures, if we're putting something like one token in an LLM, let's say an A, and that's our input prompt, right? The LLM is doing something in behind, and we're getting back something called like a cat, right? And this is what the LLMs generates us. And then we're putting the full 2 tokens now, a cat again to the LLM, and then we're getting back like a cat set, for example, right? So we have 3 tokens to make it easy. And again, the wasteful thing is that we're doing the same thing. We have here a cat, and we have also, after the LLM is doing the second time, this a cat, right? And this is something we need to take care now if we're implementing the cache, that we eliminate here this double computation of these tokens. So if we see the waste in action, and I was talking at the beginning from this IDX, so our sequence here. So the sequence at the beginning is a cat. The sequence length is t equals 2. And in the code, you will see that k in the attention calculation is a k vector of a and the k vector of cat, right? And for v, it's v vector a and v vector cat. And our output, so the model predicts that the next token is set, and then we appending to our sequence now a cat set. And then we're doing it all over again. So in the next round of our loop, it looks like this. The model receives then a cat set with the sequence length of t equals 3. And now what is red, right? We're running complete fresh without memory here, the attention. So again, k vector a, k vector cat, and then the new thing, k vector set, right? And the same for v vector a, v vector cat, and v vector set.
And it's done for every of the attention blocks, right?
For every block, it, like for all of them, it's doing this all over again without any cache. And this takes time because like this is now 3 tokens, but let's say you have 96,000 tokens, right? Then you have a lot of things to do. So, this is why the generation starts fast and gets progressively slower, right? And if you remember, like a few years ago, that this was like your if you're chatting with something like ChatGPT, right? At the beginning, this was also very, very slow. That you're getting responses, right? Because people need to start to train, to update the cache implementations here. So, and the interesting part here is that the complexity, what we're seeing here is quadratic, right? And what we need to do, or what we're trying to do with the cache is we need to remove this quadratic thing here and trying to make it linear with the implementations. So we need to set in cache, and we need to give the attention layer then with the cache memory, right? That we don't need to recalculate everything again. So, and to show this for a second, again, it's the same implementation here with a few changes. So, and I see this, we will see this in a few slides also in detail, but in the generate block here, right? So the entry, we're getting the IDs here and requesting want to have the request for the max new tokens. You will see now that we implemented something we call pre-fill, right? So with the prompt you're setting, we're starting to pre-fill the cache, right? And when we're pre-filling the cache here, and this is technically this here, we starting with our cache that all the next decode steps can use the cache already, right? So was ist Kubernetes? We put it in the cache, right? And then it starts here in our decode phase that we only compute one more token, right? And if we have one more token, we put this one more token also to the cache. So we only taking care then of really like the computation of one token. That's it. And that's the idea here when we're putting in the cache, right? So to make this clear how this works. So prefill, and you will see later in Kubernetes why this is really interesting that we can have here split in the cache implementation between prefill and decode. So when we have the prompt here, a cat, right, we're starting with the initial cache. And then we call it in the implementation past KV, because this is like the initial cache implementation here. And then you will see we have a few more variables available, k past, so ka and kcat, and vpast for va and vcat, right? So in the decode pass, right, on the intention side then, the interesting part here is we only want to have minimal input. And I was saying earlier that the newest token is the only thing we want to compute, right? And we want to have the sequence length only t equals 1, nothing more, t equals 1. That's what we want to get. So the minimal computation is then q, k, and v only for new tokens. And then we're retrieving everything from the cache, right? So we're asking the cache for all the previous key values we already have inside. And then we're starting to concatenate, right? So we're appending new KV tensors to our cache ones, right? So we will see then in the implementation something called K full is the concatenate of our K past and our K new, and V full is concatenated of V past and V new. And then we attend it, right? So we have for Q a new, Q new, and we're attending then K full and V full. And at the very latest thing, we're updating the cache, right? So we need to save the K full and the V full for our next step. This part 6 here is a little bit tricky if it comes to multi-users, because we need to also make sure that not the cache from one user will be available for the next user, right? So at some points in the implementation, you will see that we need to make sure that the cache is cleared between user sessions, right? When they're interacting with the LLM or with our model. So that said, when we're seeing the cache in action, so the model is now only called with set, right, as an input, because we have one, right? And the minimal computation then inside is the sequence t is equals 1. So q new in this case will q set, q new is k set, and v new is v set. And then we will starting to retrieve and concatenate again, right? So the k full is then ka, kcat, and k set. And the v full is va, vcat, and vset. So and the intent we only query against like q new to get k full and v full that we can get this. So and then the interesting part here is we eliminated our quadratic issue here, right? So OT is only now OT and it's linear, right? So and the idea here is prefill once and then decode fast. And I can show this now in action a little bit. So let's make the same thing what we did at the beginning, but now, so again, 10 tokens. And for 10 tokens, you see now on the left side without in KV cache, and on the right side, you see it within KV cache, right? And you see here prefill, right? Yeah. And prefill takes a little bit. And the difference with 10 tokens now is a millisecond between the steps, right? Between the tokens. So if we would technically do now, let's say we're saying make 500 tokens. Then you see on the right side that it's for every new token generation round about 1 millisecond, right? And on the other side, it's for every new token, I don't know, at around about 20 milliseconds per new token, right? And the cool part, what you're seeing now here is without the cache, we have 311 words, right? It's garbage, but with cache, we have also 311 words, and it's the same garbage, right? And the cool part now is you're seeing that with the cache, we have the exact same output. So it's working that we're caching here the thing. So that's it. Let's come back here. So it's cool now that it is working here locally on my machine within KV cache, but we just built this now for one GPU and for one user, right? And the production looks totally different with you hosting the models on it, right? So let's say we would start hosting my GPT in a Kubernetes environment, right? And the first thing, without checking what's currently available, let's use the deployment, let's use the service, and let's use a horizontal pod autoscaler, kubectl apply, and then we are done, right? Because then it's running. No?
Storage.
For what?
For KV cache.
Yeah, what you're thinking of, how many storage you need?
Depends on the model size.
But let's say I have a GPU available now. What you're thinking about? The GPU has, I don't know, 80 gigabytes of storage available, and I put my KV cache inside.
What do you mean, sorry?
The GPU already have storage, right?
Yeah.
So I can put my KV cache on the GPU.
Yeah.
Yeah.
But Kubernetes is not built to do GPU multi-tenancy, so it's like the basic. So you need to consider GPU when you want to do scheduling, sharing the GPU among different tenants, and so on.
Okay, so the first thing was what you're seeing here, let's say with service and horizontal pod autoscaler at the beginning is, let's say, make it easy, right? We have now a pod which serving my model, right? And I have 96,000 tokens, right, of my context, and this arrives, right? And the service in Kubernetes makes now round robin and put the request to pod A. Pod A starts building the KV cache and it answers, right? And it works. And if it's only like one pod, I can send again a request, I have my KV cache and everything is fine, right? But if now the horizontal pod autoscaler kicks in, right, and makes now 2 replicas out of it, right? What happens then with the second replica?
You can't find the GPU.
Perhaps it has enough CPU available. But
the smaller one gets killed in favor of the larger one, and now you cache miss at the larger one probably.
Yeah, it's relatively easy. With round robin, you see like we're coming to a new pod, and the new pod has no idea of our KV cache. So you need to take care now. What does it mean, right? And let's say, cool, we have horizontal pod autoscaler, and you start adding more and more replicas here, right? Cool, but that's even more worse because you really start to computing the 96,000 tokens again and again and again in the different pods, in the different GPUs, right? Because there's nothing available per default in Kubernetes which taking care of KV cache, for example, right? So if then request is coming to Kubernetes, right, what to do now? How I can find out from my prompt and from my generated tokens out of it, right, which pod is the right for me, that I can get the right KV cache, that I can starting only generating like this one more token, right? Yeah, and that's what we already talked about. Also, rolling update is a really rolling upgrade is also a problem, right? Because your KV cache will gone after the pod is done. You need to think of how you can get the KV cache back, or how a new instance will get the KV cache, right? So, and in Kubernetes, they started round about 2020 to figuring out problems to solve in Kubernetes, right? One of the things routing. So how we can assure that the request of the pod with the cache is the right one, right? And the other thing is storage. And storage means storage for our KV cache at the end of the day, right? But storage also can mean like whatever the model needs as inputs needs to be available for the model. So, and I call it like the cache roulette, what we're seeing at the beginning. And this is like everything, all the projects we're seeing now in a bit started because of this. Because in Kubernetes you get the cache roulette, because nothing is aware of how the KV cache can be bound to other pods, how the traffic can come to the right pods. So let's first, before we introducing the projects, talk about prefill and decode, because I already did this and there was some questions in the pizza pause already. So you are seeing that we pre-filling now and we decoding, right? And the prefill technically builds our KV cache from our prompt, right? And this is now really compute bound, which means you need to run it somehow on a GPU, and the GPU is only taking care then, because it needs the flops, to pre-filling, right? So all the other small jobs from the decode will pause for a second on the GPU, right? The GPU is only taking care then on this pre-filling.
So it's doing this attention matrix, this giant attention matrix.
Yes.
Lots of calculations.
Yeah, and that's doing it, let's say, for 96,000 tokens, perhaps for seconds, but thinking about you have millions of tokens. So for an amount of time, your GPU is only doing this prefill, right? And it's cannot do something for decode. So all the decode part will wait. So for that, in the decode thing, we read the KV cache in decode and we generate the tokens, right? And this is only memory bound. So technically there was the question before, do we really need the GPU for decode? I don't know. There are other projects outside, they're saying they can run the decode on TPUs, on special accelerator cards, whatever. The only thing which takes care here is bandwidth, right? Because you need the bandwidth here. And this happens here 1,000 times per response, right? And you get every milliseconds, like you're seeing this from my demo, right? You get every milliseconds tokens. And you can generate thousands of tokens here in parallel. But for that reason, the KV cache here needs to be transferred, perhaps. We see in some projects later that they're running prefill on this GPUs and they're running decode on other GPUs. But for that reason, the KV cache needs to move around in your Kubernetes cluster somehow. The other thing is, which is relatively common, and let's say 96,000 token of context can be 48 gigabyte of KV cache for one user. It's true that there's a lot of projects available outside to shrink this 48 gigabyte to something different, right? What we talked about? 6 gigabytes something with a few...
Yeah, some models don't do complete attention on every layer, but every 10th layer or so, and then you already have tens of that. So you can optimize all the models.
Yeah, you can.
Magic.
Yeah, exactly.
But it's gigabytes for sure.
But you're seeing like a GPU has what we said, like 80 gigabytes, for example, right? So you can now make the calculations to users. Then that's it, right, for a GPU. So, and for that reason, there are, in the projects, we will see that there are mechanisms available that you can transfer the KV cache out of the GPUs to the memory of the CPU. You can transfer the KV cache to SSDs. You can transfer the KV cache to object store. And to make like an example, let's say a user is idle for 5 minutes. Do we really need all this KV cache stuff inside the GPU, or can we move it to the CPU RAM? And the same thing is the conversation from yesterday in the RAM, or can we put it on SSDs? If it's like a longer thread, can we put it to object store and can we restore it later, right? And it all depends on your users, which they're interacting with the models, right? If you have like all the users doing the same thing, cool. Then it's like this our one user, because everything is in a KV cache and we have like a small computation, right? But if you have like random users and everybody's doing differently, then you need to really take care of what's happening in your KV cache, right? Yeah, and the interesting part here, like cache lifecycle is not conversation lifecycle, right? It's a bit different, but you can make the analogy here. So
I have a question. So in ChatGPT or in Germany, you have these history of chats. They're not storing 48 gigabytes for the history. They just store the text, right? Or
depends on the time when you look, right? When you chat and 5 minutes
Then
later,
it's
you have
inside.
the KV cache. Eventually, it's gone.
yeah,
it's gone. You have this in your. Let's say if you would use like your Cloud Code chats locally, right? You have like all the things in JSON file blobs on your local machine, and if there's no cache available, they're sending all again everything.
and when they're pre-filling again, yeah.
The request always has everything, like the whole.
Yeah, everything's
Whatever.
inside. They're sending all the time everything over the internet, right? And then they're starting to figure out when they're sending the prompts, they're making the tokens out of it, and then they're starting to figure out like which token is on which KV cache where, right? And you have system prompts, for example, and you're saying like you are the nicey shiny agent ABC, but everybody has perhaps like the skill outside, right? And the same system prompts. So this is easy for ChatGPT and for Cloud Code, because this is already in the KV cache. This is nothing to do. They're only taking care what is different in your question now.
And it's
Or-
always about prefix, right?
Yeah.
A common prefix you can cache. As soon as there's just one bit different, everything afterwards is lost.
Yeah.
To the computer.
But
Cannot share.
when it starts to make a difference.
So they're
And before
optimizing.
it's,
Yeah.
so we will see perhaps in Kubernetes and in CNCF and Linux Foundation, the first project which started around about 2020. They started with as KServe, and then it started by Google, IBM, Bloomberg, NVIDIA, and Selden. You probably know Selden from Kubeflow, right? And if you're looking deeper in KServe, then you will see that a lot of things from Kubeflow are implemented at the beginning in KServe. They donated it to Linux Foundation, to AI and Data Foundation first, right? And then they renamed to KServe because they wanted to go more to this Kubernetes mainstream something, right? And then last year they donated it to CNCF, and they're already incubating because it's a project which is widely used outside. That's the reason why they're incubating. There was not steps before because they approved like sandboxing from Linux Foundation before, right? So they said like everything is fine. So technically, you will see here, KServe can deploy the models. It knows a bit of KV cache. They're using another project for it, LM cache, and they're using for auto-scaling KEDA, right? So probably people of you knows this already. So we will see technically client requests coming. They're sending it via some Envoy AI gateways to the Kubernetes cluster. They have vLLM as engine here running, and then they technically have GPU nodes and the KV cache available. And because of they're using LM cache since a few months, they also can offload the KV cache to CPU RAM. But that's technically it. You will see here that they start to creating something they call it like an inference service CRD, right? So they have a very light inference controller here running, but it's only like building Kubernetes manifests together, deploying in the background like Kubernetes deployments, configuring the vLLM for the model, and then they're taking care of like configuring of LM cache, that the LM cache will be available for all the vLLM pods technically. And you will see in the community that they're trying to add more and more here on the control plane side, because multi-node is a big problem. They have a problem with prefill and decode that you can split it. They never implemented it. They have very few alpha implementations out of it. But technically, they're doing like the prefill and the decode on the same GPU at the moment. And this is like wasteful, right? And you will see that other projects are doing it differently. So technically, there's another project outside in the CNCF. It calls llm-d. This was founded in 2025 by Red Hat, Google Cloud, IBM Research, CoreWeave, and NVIDIA. And then they're becoming like CNCF Sandbox at the beginning of this year, right? So Red Hat was really pushing it to the CNCF, that people start sharing implementations out of it. You will see here a lot of more boxes in purple. So they have an own inference gateway. They have an own endpoint picker. They have a LoRa router. I will come in another project what this LoRa router is doing. They have here the option that the vLLM can split prefill and decode on different GPUs, right? And you will see the GPU nodes here. They can host the KV cache, and they have the full options to offload the KV cache to CPU RAM, to SSDs and S3s. They have also Nixle available, right? The interesting ideas here with Nixle is that you can transfer KV cache between GPUs, so you don't need to put it like outside of the GPUs. You can transfer it between the GPUs. There's also InfiniBand available under Nixle as one thing, so that you can get access from one GPU to the other GPU, KV caches. All this kind of stuff is behind this Nixle. And here they have something, they call it like an inference scheduler and a workload autoscaler, right? So, and this workload autoscaler here, they're trying to understand what's going on in the decode and the prefill phase and how they can like autoscaling this. what they need for different models here. And for the inference scheduler and the endpoint picker, we can have in a bit look what this means. We will see from another project they have something similar. So technically, when a prompt is reaching the Kubernetes cluster, it goes over in Gateway API, right, from Kubernetes. And then they have something called an endpoint picker available. And probably Stefan has a lot of more details what this endpoint picker is doing in detail. But technically, the llm-d guys, they have a scheduler, which the endpoint picker is asking. They have the KV cache here. And in the KV cache, they have an indexer. And they have an KV block index. So they can query indexes. And then the idea here is when the prompt receives the gateway API and the endpoint picker, right? They're making tokens out of it. And with these tokens, they're asking now the KV cache indexer and the KV block index, which vLLM pod has already the KV cache for me. And then they're giving back in score of the pod because parts of your tokens can be hit different KV caches in different vLLM pods, right? So that's why you're getting
prefix,
the score.
right? The longest prefix, which is somewhere.
Yeah, and they're scoring it, and then the endpoint picker can decide to which pods they're sending the request from you. And on the vLLM pod side, you're seeing they're emitting something they call KV events, right? And via ZMQ, they're subscribing here to an K event pool, and they're updating the index. So whenever the vLLM pods generating new KV cache entries, right? They're sending it over here to the index, and it can be then available for the endpoint picker. The bad thing here is it is decentralized, means every scheduler, and a scheduler can also like scale up to multiple instances, right? But every scheduler maintains its own view of the cache. And that's bad because if there's a rolling upgrade of one scheduler, and you're hitting with your prompt like a scheduler, which is started completely fresh, then he has no idea of the other KV caches at the moment. And this is the big difference to another project we're seeing in a bit. Just here, because that's also an interesting project here. It's 2024 founded by ByteDance, and that's TikTok at the end of the day, right? And ByteDance moved the project in 2026, around about end of January, at the beginning of February, under the vLLM organization, because they're doing tons of implementation in vLLM engine that they can tune, fine-tune, whatever they want to do with models. And you see on their side, they have tons of implementations running here on their control plane side, right? And here's again this LoRa router, right? And this means low rank adaptation. So technically, Stefan showed a bit, you have weights, right? And you can update the weights on the fly in models for fine tuning. So let's say you have multiple, let's say multiple organizations want to get from you the same model on your cluster, right? And you can now host the model multiple times, but this means I wasn't fast enough. But that means you need to have for every model a lot of GPUs available, right? Multiple times. But you can start with this low rank adaptation to hosting one model and only fine tune based on your companies which come in there. So let's say you have a Japanese company and a German company, you're only hosting one model, and then you're updating the weights based on like Japanese and German. That's it. And you can make it on the fly. And that's what they're doing here. But then the LoRa router needs to understand in which vLLM pods on the Kubernetes cluster is now the right one for this LoRa updated weight thing, right? That the Japanese requests coming to the right pod with the adapter for Japanese, for example, right? Other interesting part here is they have cold start managers and pod deletion managers. They need to take care on how they saving the KV cache under the hood. I not hit it here because they late implemented it. They have a distributed KV cache runtime, which is not running on the GPU nodes, but outside, right? But for that reason, they need to taking care of cold start. So new vLLM pods coming up, this cold start manager needs to grant them access to KV caches which are available. And for pod deletion manager, they also need to take care that the KV cache is in the right state before they can shut down the pod here. Yeah, I think that's the interesting part here. So then NVIDIA Dynamo, they also created a project in 2025. They reached, Stefan can correct me, but I think at the beginning of 2026, the V1 version for production release from Dynamo. So if you're seeing this picture a bit, it's very similar to vLLM, because vLLM started to llm-d. So yeah, sorry, to llm-d, because with the latest release, they technically implemented everything what Dynamo also did. So they have now prefill and decode, they have Nixel implementation, they have the KV cache memory here, they can offload. Basically the same thing what Dynamo also doing. Interesting part in Dynamo here on the control plane side, they have something called a Dynamo planner and have a smart router available, right? And again, for the routing, looks very similar what you're also seeing in llm-d. But now the KV routing here is centralized, right? So technically the smart router here is asking a KV indexer if it find matches for the request, right? And they call it like a radix tree. So here's a tree available that they can walk with the tokens, right? And if they found a matching tree here inside, they also sending back which kind of worker is responsible for this KV cache. And why it's a worker, Dynamo has different, what's called engines available, vLLM, SGLang, and TensorRT, so they can run multiple different model engines in Dynamo. And for that reason, in Dynamo, they need to take care that all the workers here emitting KV events, right? They're doing it via nets here, and they're updating the tree here. The cool part here is because it's centralized and it's a shared radix tree, it's the source of truth for all routers, right? Means if a router is starting up again because they're scaling it up, the first thing what the router is doing, it's asking like the radix tree, like, hey, I'm new, what is the current state of the trees? And then it can start walking. So that's like the big difference to what we're seeing in llm-d. Yeah, that's technically for if there's time later, we can have a look. There's tons of YAMLs how to configure this. This feels like a little bit like the beginning of Kubernetes, that you have, I don't know, 1,500 lines of YAMLs for a deployment, for example, that you can really configure all the things you need for an vLLM. But there's one thing we not talked about today, and yeah, KV cache is not encrypted. So technically, the KV cache in the GPUs is there. So the prompts we're sending over TLS, right? But the cache is completely plain text. And also, a lot of projects inside the Kubernetes cluster, they're doing everything plain text. So they're hoping that the encryption is under the Kubernetes, so in the Kubernetes world, right, between the nodes. So, and the cache is our prompt at the end of the day, right? Mathematically. So there's a few guys outside, they started if they can recalculate the KV cache to the prompt, and they had success. There's a whole article from the end of the last year available. So technically what you need if you have access to a Kubernetes cluster with the KV cache, you need to open weight. The easiest thing is open weight models, right? You can go to Hugging Face, get all the weights from Hugging Face, and then you can start to invert the KVs you have already in the cache, right? And then you can recover the input embeddings here. The next thing you can do is like guessing tokens. So you can generate local KVs, and then you can start if you have matches inside, right? In a remote KV cache, then you can start matching it, and then you can also start injection, right? So you can see repeat the previous contents completely, and then the model starts echoing everything out if you have access to a Kubernetes cluster. So this is all the actions you can do with the KV cache outside. So means whatever sensitive information you're sending via a prompt, the guys who are hosting the models, they can technically recalculate whatever is inside. Yeah, that's technically it. If people are interested in like tons of YAMLs, I think AIBrix is sometimes interesting with tons of YAMLs. Yeah, for example, you see, for example, this AIBrix guys, they have Ray cluster fleets. Perhaps Stefan knows this a bit. There's other projects in Kubernetes around which taking care of fleets of pods, right? And
Make it a bit bigger.
I can try it, but I can like this. Cool. So you have a cluster fleet here, for example, available, right? And then you can see like whatever you can configure here. CNI configs, runtime configs, whatever, right? So you have tons of configurations available. It's only like for the fleet now, right? And you have these configurations for a lot of other things too here. Yeah, because we talked about this, you see that for LMM, what is this? Yeah, in llm-d, for example, you can say, okay, you have something they call model artifacts, right? So you're saying, okay, this model, you get it here from Hugging Face, that's the size. You have then routing if you want to enable proxies here or not. For the decode phase, you can have configurations for prefill, for multi-node, all this kind of stuff. They're handling most of the stuff via config maps. I think this is something Stefan knows a bit better than me. So they have in Dynamo something like graph deployments available. So some things I personally don't like is that they have like capital characters here at the beginning.
Yes, it's better API coming fixing that.
So yeah, that's something like, okay, I was the first thing like, ooh. And technically you can configure like what you would configure on the pod, right? So leftness probes, readiness probes. They call it an extra pod spec. So the main container gets a specific image, workds, and specific commands that they're running for example, the vLLM under the hood. So whatever it is, right? So what?
Hello world worker.
Yeah,
Just example.
These examples. So technically, they have different workers, right? And they have specific names, and then you can set this. So yeah, and perhaps they're doing in the future here something like the full pod specs.
It's becoming pod spec.
Yeah. So because at the moment, like the API is sometimes a little tricky because it's not a real pod spec. You need to figure out now this is liveness probe, this is this that you can configure. I think that's it.
While you did the architectural overview of the different scheduler systems, llm-d and Dynamo, so there's also Ray and other forms of older HPC. How do you see that, which don't work on Kubernetes or do work?
So what I can say is what I'm seeing in the Kubernetes community at the moment is that all of these projects are around. And they're trying in a few areas to converge things, but a few projects only using it as puzzles. So if they're seeing like this solves today a specific problem, cool, take it and roll it out, right? It's only like the next 2,000 lines of YAML and then you run it, right? But there's if you're seeing like a Slack channels from different projects, right? There's a lot of conversations between them. They're trying to converge stuff.
And everything here is inference, right? This is converging to Cube, it seems.
Yeah, inference.
For training, there's Swarm and others as well, and they're strong as well. But inference is just getting bigger and bigger, much bigger than training.
About the GPU memory, what just came to my mind, what component in Kubernetes or GPU driver clears the memory if one pod crashes and another one takes over the GPU? Or could I read it out what's from the former model inside?
That's a CUDA question, I think. Not Kubernetes, that's low level.
That's a driver.
The operator knows it. And
No, it's much low level. So he didn't mention vLLM, right? This is the engine. This is basically, so we showed PyTorch. He showed it, I showed it earlier. That's for training definition. vLLM is Python-based plus Rust and C++ engine for surfing. And this speaks to CUDA. So this is just the memory management and stuff.
Yeah.
So technically, if you're losing a pod, they're still overriding what is inside the GPU instead.
Yeah, if I don't want to override it, I want only to read it. That's the question, huh?
So I'm not aware that someone is doing this.
So let's say if I want to start building a Kubernetes scheduler for a KV cache aware, GPU aware scheduler that does all this calculation and stuff, what needs to happen at the node level? Like, does the Kubernetes API need to be aware of anything that is, for example, Dynamo scheduler?
There's a big topic about gang scheduling.
Yeah.
Like the examples of Dynamo, like there's a front end and worker and so on. And those are often pods which are bundled. So they have to land on the right nodes at once. If one is missing, the whole system doesn't work.
The gang scheduling is taking care that they're only starting to really allocate the memories and CPUs and GPUs if everything can be deployed at once.
So it's all or nothing. Yes.
Yes,
And
because if you would, let's say you need 100 pods, let's say, right, and you can schedule 80, but the other 20s are missing, then you're starting to waste, right? Because you start deploying the 80s and the other 20s, you're waiting and waiting and waiting. And with this gang scheduling, they're really taking care if they can deploy it or not.
And there are special scheduler extensions. So there's this Kai thing, which is a custom scheduler basically. And there's like a deployment for pod clicks. This is so it's called Groove in Dynamo. It's a special high level like a deployment for this kind of workloads basically. And there are a couple of those. And there are also conversion because Kubernetes is learning a workload API at the moment. Mm-hmm. So where you can express the pods belong to a group of pods. So it's coming.
There's a lot of folks working on this.
At the core group, things are changing.
Yeah.
In Kubernetes?
Yeah. A pod has a reference to this workload thing.
They already started to adding stuff, right? So you see this in the latest Kubernetes releases. If you're reading it between the lines, alpha features and all this kind of stuff, they're putting more and more in. You probably don't see it like on the big cloud providers because they're disabling all the alpha features, right? But if you like looking at them, then you see it.